I'm pleased to welcome you to our inaugural symposium for the Chemical Review's Thematic Talk Series. This series is designed to highlight significant and timely topics that are featured in thematic issues in chemical reviews. So the symposium today is on the thematic issue entitled Advanced Materials and Methods for Catalysis and Electrocatalysis by Transition Metals. And we are going to feature one of the guest editors and four of the authors. So to start out, first I welcome Professor Yunnan Jia from Georgia Tech to give the introduction.
Okay, so can you guys see the slides? Okay. All right, good morning from Atlanta. Welcome to the
Not yet, I don't think we can, I can't see the slides.
You don't see the slides? Okay, let me see. Let me somehow, okay.
The green button at the bottom.
I did, let me see. In time.
Click on it. Okay.
That's looking good now, yeah.
Okay, all right.
Now you need to share the slides instead of the
So is it okay now?
That looks very good. Thank you.
All right, so nice to meet you all online. I hope everybody is doing well and life will go back to normal very, very soon. And this webinar is based on a thematic issue published by Chemical Reviews early this year. And it was co-guest edited by me with Professor Campbell from the University of Washington and Professor Walden Pyongyang from Fritz-haber Institute and Professor Margaret Karpis from the University of Wisconsin-Madison. On the behalf of all co-guest editors, here I would like to thank Sharon, Tal, and Jamie from the journal office for their help and the support in keeping the publication of this thematic issue on schedule despite the pandemic. In organizing this thematic issue, we aim to bring snapshots of exciting and timely research in heterogeneous catalysis and electrocatalysis to the community. And during this webinar, you will hear brief presentations about 4 of the 9 published articles. Because of the pandemic, 8 manuscripts were delayed. So these manuscripts will still be published in chemical reviews in the near future and virtually linked to this thematic issue. So for more than 1 century, catalysis has been a major contributor to the world's economy. And more than 85% of the chemical industry now is built upon different types of catalytic processes. At the current stage of development, these processes are dominated by heterogeneous catalysis, and which contribute to more than 80% of all the catalytic process. In this case, the catalysts are typically presented as nanoparticles on solid supports that could be made of oxides, nitrides, and carbon materials, and so on and so forth. So in general, heterogeneous catalysts are fundamentally troubled by a number of issues, including heterogeneity on the surface and the complexity in terms of atomic and chemical structures. So as you can see, this is a typical TM images of a commercial PTC catalyst. Basically, it's platinum nanoparticles supported on carbon. And for these nanoparticles, as you can see on the right side of the high resolution TM images, the atoms on the surface are going to be situated on in different types of environments because of different coordination environments. And typically, the atoms could be on the vertices, edges, bases, and so on and so forth. And what makes like more challenging is that these nanoparticles can also contain like defects. This could be kinks, steps, vacancies, and so forth. So that makes it very difficult to really describe heterogeneous catalysts. So for these reasons, people have turned to model catalysts based on single crystal substrates or thin films that could be fabricated with well-defined atomic structures on the surface. And this kind of studies have already led to development of a field known as surface science. And despite tremendous success, the use of single crystal substrates, however, are naturally troubled by something we call materials gap, okay, between heterogeneous catalysis and traditional surface science. And this gap can be potentially closed by combining surface science with colloidal synthesis of nanocrystals with well-controlled shapes and the surface structures, as described by one of the review articles we published in this thematic issue. And there's also another gap known as a pressure gap for the knowledge between traditional surface science and the heterogeneous catalysis. And to a certain extent, this gap can be contribute to the limited capabilities of most catalytic most analytical tools for probing the surface in the presence of gases or liquids under ambient pressure condition. And this gap can be closed by developing surface-sensitive techniques that do not require UHV conditions, as you can see from some of the articles published in this thematic issue. And lastly, I also want to point out the traditional definition of a catalyst had to be revisited in recent years. And this is due to the advancement made in the development of more sensitive techniques for in situ and operandi characterizations. And now it has become evident that the catalyst, in fact, evolves during the catalytic process, and that the structure and the chemical changes that it experiences are not always reversible and might lead to deactivation of the catalyst. And these new findings further demonstrate the need to integrate the research efforts in both materials and techniques for the development of optimal catalysts tailored for the specific applications. And here I just want to quickly show you what's included in the review article we published. So basically, we make an argument that by controlling the shape of these nanocrystals, you will be able to control the specific arrangement of atoms on the surface. That could be 1-0 facet for the cubic shape, 1-1-1 for the octahedra, and 1-1-0 for the rhombic dodecahedra, and so on and so forth. And by making these nanocrystals on very small size scale, at the same time with well-defined surface structures, basically you can have something that can bridge the gap between single crystal substrates and the traditional practical catalysts. So with this, I was going to stop and stop over here. If you guys have questions, I can try to answer at the later point. Okay, so let's move to the next speaker.
Yes, thank you very much, Yunnan, for introducing this thematic issue and this symposium. So the next speaker, our first full speaker, is going to be Professor Rongchao Jin from Carnegie Mellon University in the United States. And his review is entitled Toward Active Site Tailoring and Heterogeneous Catalysis by Atomically Precise Metal Nanoclusters with Crystallographic Structures. So welcome, Rongchao.
Thanks, Yuna and Sharon. Can you see my slides?
Not yet.
Probably takes a few seconds.
Yeah, it's there.
Okay, great.
Yes, we see them very well. Thank you.
Okay, great. Yeah, so as you mentioned in this special issues about the transition metal catalysis, heterogeneous catalysis. So if you look at the periodic table, actually, we have more than 50 elements. They are called the transition metals, D block and F block. And so speaking of catalysis, D block is particularly important, right? Yeah, so for example, no matter the precious metals like platinum, palladium, or non-precious metals in iron, cobalt, and nickel. So here, let me use a well-known example, the auto emission cleaning three-way catalyst. So here we are using platinum, palladium, rhodium nanoparticles to clean up the auto emissions. So that way, we can eliminate those toxic gases, NOx and carbon monoxide. Otherwise, you're going to be poison, and also get rid of the unburned gasoline, carbon, hydrogen, and stuff. So that way, we are not damaging the environment. So here's a typical TM image for the heterogeneous catalyst. We have two components. One is those metal nanoparticles, transition metal nanoparticles, and then the second component is the support in the metal silica or aluminum oxide, titanium dioxide, and those oxide materials that you typically use to support the transition metal nanoparticles. So obviously, most important thing is those nanoparticles, no matter precious metal nanoparticles or non-precious metals. So here, if you run the typical size distribution, you're going to find out that they're actually quite polarly dispersed. So for practical purposes, it's fine, as long as your catalyst is highly active, highly selective, and highly stable, and you're doing a very good job. But as Yuna mentioned, for fundamental studies, it's really important to have a well-defined system. So back in 1970s and 1980s, people started to explore those well-defined single crystal surfaces. So you have a well-defined surface structure, and then you can look into some very fundamental issues such as adsorption and elemental steps and so on. And then since the 21st century, we have well-defined nanoparticles. For example, in the case of spherical particles, we can systematically control their particle sizes. So definitely they can be utilized for heterogeneous catalysis, and in many different shapes. So as Professor Yunnan, he has done tremendous work in this field. So all these are really good in new kind of a model system in addition to the single crystal surfaces. But there are still some sort of fundamental issues. So one is the precise structural activity relationship at the atomic level. So for example, let me use these highly monodispersed nanoparticles in a 5 nanometer average size, right? So they're highly monodispersed. But if you look at them one by one on the high resolution TM, they're not really the same. So for example, the first guy is spherical, second is polyhedral, and then we have a 5-fold twin particles as well. So they, the low mag in the TM, they are highly monodispersed, almost the same. But if you look at them one by one, they're not really exactly the same. So that's kind of, for most purposes, yes, it's fine, it's not a big issue. But again, if you really want to look into some fundamental issues, this could be a concern. And the second is, use TM, yes, you can clearly see the atomic lattices, but the surface structure, for example, the first atomic layer, or how those stabilizers, protected the particle surface, forming chemical bonding with the surface, or in the second, first, atomic layer. So that kind of information we don't really know. But in terms of catalysis, as you know, the surface is very important. Because the molecules come down and they land on the surface, the older bonds get activated and broken, and then proceeded to the chemical reactions. So we really needed to know the surface structure, surface composition, and so on. So our motivation is trying to create atomic precise nanoparticles, and then further solve their total structures. So that way we know everything, what's on the particle surface, and how those surface stabilizers protect the metal core. So we're trying to utilize these well-defined nanoparticles as new kinds of model catalysts. So in that case, it would be possible to look into the precise dependence. So typically, as you know, the smaller particles will be more catalytically active because they have a larger surface to volume ratios. Yeah. But in some cases, it could be a optimal size. Yeah, so smaller is not so good. Yeah, you have to go to the optimal size. So if you can find out that kind of an optical size, and then obviously you can dramatically improve your catalytic performance, the performance of the catalyst. Right? Yeah, so you just go to that particular size. And then, so based upon the well-defined nanoparticles, it will also be possible to really look into the fundamental issues of atomic structure and electronic structure and their correlation with the catalytic performance. Yeah. And then ultimately the active side structure. Yeah. Okay, so in our review, we sort of focus on the atomic precise nanochemistry approach. Okay, so first is to create those well-defined nanoparticles, as I mentioned. So here we have a couple of major goals or aims. Okay, so one is atomic precision, and the second is molecular purity. Okay, so when you prepare nanoparticles in solution phase, often you're gonna have some impurities, side products, excess ligand stabilizers, in your solution. So, but in our case, we're trying to get rid of all those garbage to clean up the nanoparticles. Yeah, so that way you will have no concern, whether those garbage molecules are contributing to your catalysis. Yeah, so in some sense, these well-defined nanoparticles, they behave kind of like a molecular compounds. Yeah, so like organic people, they make whatever drug molecules or and the biotic molecules. Yeah, so they are well defined. Okay. And then in this case, so this is a mass spectrometry. I'll go to the 5, the first size our group worked out. And then in recent years, my student also pushed to the larger sizes in hundreds of atoms. Yeah, so obviously it becomes more difficult, but my students really did a great job. And then the method can also be extended to other metals, not just the gold. You can also extend it to silver and alloys, and many systems. Yeah, so those are all very useful for heterogeneous catalysis, nanocatalysis. Yeah, so far, I would say the size range from tens of atoms to hundreds of atoms, roughly speaking, from 1 to 3 nanometer are now possible to achieve atomic precision. Okay, so these are can serve as model systems for nanocatalysis. And then many molecular analytical tools, for example, NMR, you can use. Yeah, but if you have polydispersed nanoparticles, it's going to be tough to utilize the NMR because you're going to see very broad peaks and not really much useful information you can obtain with NMR. Most important thing in our case is, once you have these atomically precise nanoparticles, you're going to be able to arrange them into a macroscopic crystal, for example, millimeter size single crystal. And within such a single crystal, you have billions of nanoparticles nicely arranged up, for example, in the setting face to face. So that way you can do X-ray crystallography and eventually map out everything. Yeah, so not just the metal core, but also the surface ligands, how those surface ligands stabilize the metal core. So here, let me give you one example. Yeah, so here we have a truncated tetrahedra as Professor Shah. He makes a much larger ones, all right? Yeah, but this one is a much smaller, only about 1 nanometer in size. Yes, it's really at the bottom of nanoscale. So you have this truncated tetrahedra, and by using X-ray crystallography, you're going to be able to map out everything. So how the surface get stabilized by ligands. Yeah, so in this case, we have this kind of a very special surface motif we call diagonal staple. If you have 2 gold atoms, substitute gold atoms. And if you have 1, we call monomer staple. This is kind of jargon. Yeah. And then ultimately, the total structure. So you can also map out, the carbon tails. And so this is a gold 36, which is relatively small. And then, as I said, in recent years, my student and also some other groups, they were able to push up to the much larger sizes, hundreds of atoms. So TEM, as it's really important for nanoparticle research, and typically, we heavily rely on TEM to measure the particle size and measure the particle shape. But for ultra small nanoparticles like 1 or 2 nanometer in diameter, in TEM is not so useful. I mean, you can still see them, but it's not really possible to precisely determine how many atoms per particle and what's on the particle surface, what's the bonding mode, right? And so here, let me give you one example. In this case, we have a spherical gold 25 and the one-dimensional or gold 25 nano rod deposited on the support. And so they look the same. You want to be able to see, oh, this is spherical, that is one-dimensional. And so only by X-ray crystallography will you be able to precisely nail down every atom, every ligand. So that's really the beauty of X-ray crystallography. So far, for example, many different sizes, many different shapes, and then also the isomers, available for catalytic research, for fundamental studies of catalysis. And so in our review, we sort of summarized several topics, And so the first way, the straightforward way to utilize those well-defined nanoparticles is to, for example, you just take those particles in solution phase or deposit onto some supports for dispersion and stabilization. And so here, for example, let's say you can utilize these particles to generate singulated oxygen. And in that singulated oxygen, as you know, highly reactive, right? So you're going to be able to oxidize whatever organic substrate. And in that nitro reduction, and then also the hydrogenation, and then a clicker reaction as well. So there are many examples. You can go to the review article to find more examples. So in this case, typically, if you want, you can use mass spectrometry and also UV to confirm, whether the initial particle size got changed or the structure got changed, because the UV is sensitive to the structure, sensitive to the size, and also mass spec tells you the molecular weight of your nanoparticle, whether there's any change in size of reduction or size change. So that's the most straightforward way you can utilize these well-defined nanoparticles. And so typically, because if you have ligands on a particle surface, the activity is usually more or less suppressed. So if you prefer to kick out one or few ligands to increase the catalytic reactivity, that works. So in this case, you can, for example, kick out 1 or 2 surface ligands to expose, to fully expose, the surface side. And then, of course, if you really hate ligands, you can kick out all of those ligands by whatever thermal treatment or some other redox treatment. And then finally, you can also utilize these nanoparticles to make new kinds of nanocatalysts. So these are the sort of different ways you can utilize atomic precise nanoparticles. So with these well-defined systems, you can really look into some very fundamental issue, for example, size effect and structure effect at the atomic level. So starting from, for example, if you are interested in the carbon tail, whether different carbon tails have effect. You can design the same size, same structure, but use different carbon tails, to protect the particle. And then there are many examples. So we also give examples in the review article. So for example, the semi-hydrogenation reaction, and then the CO2 conversion, and then the support effect as well, taking effect. So there are, I think, a few quite unique things you're going to be able to achieve with these well-defined nanoparticles. So here, let me give one example. We call correlated pair. So here we have 2 kinds of gold 28. So they have the same size, 28 atoms, same inner core structure. But the only difference is the surface structure. So here we can use a very simple reaction, carbon monoxide oxidation, as a model, right? So you can see they have different catalytic activity. So with the ligands on, but if you remove the ligands, they become the same. So that kind of makes sense, because if you remove the ligands, that bare gold 28 will adopt the same structure. Because it's really, the kind of beauty you're going to be able to utilize, you're going to be able to achieve by designing such correlated nanoparticles. And so we can eliminate those entangled factors and just focus on one factor. So you can really look into the effect of that particular factor. For example, whatever surface structure or size. Yeah, and then as a Professor Shah mentioned, that bimetallic nanoparticles are particularly attractive in catalysis. So in the field of atomic precise nanoparticles, Negotiate group, they have done very impressive work. Yeah, so they were able to even isolate, different isomers. For example, let's say 2 Ag atoms doped into gold-25, and then they were able to isolate the different isomers. Yeah, so the 2 Ag atoms could be close to each other, could be far away from each other. Yeah, so but they're the same size, the same structure, right? Yeah, so it's very tough to isolate, but they amazingly worked out. And then in terms of catalysis, yeah, so some groups worked on.
Okay, Rongchao, like 1 more minute.
Oh, okay, yeah. Yeah, so so in this case, we can look at the catalytic reactive one atom at a time. Yeah, so you're going to be able to achieve quite a lot of information. So there are many other systems, for example, the organic transformation, and then photocatalysis and electrocatalysis. So I will not go into too much details. So by utilizing these well-defined systems, you're going to be able to achieve a lot of experimental information. And then, as we all know, theoretical simulation are also very important. And so, yeah, here I'll give you some examples. Yeah. So remain challenges. So in the case of homogeneous system, it's relatively easy. For example, you can do mass spec, you can use this to sort of track the system. But once you deposit those particles onto the support, it becomes much more challenging to track. Yeah. So this, sort of pressing issue I would point out. Yeah. And then finally, so I would say, with these well-defined nanoparticles, yeah, I'm not saying everything is done, but it's really a new start. Yeah, so whatever you do, I think ultimately it gives us a lot of hopes to map out the active site, and then ultimately to tailor the active site and improve the catalytic performance. And so I'll stop and happy to take your questions.
Okay, for the audience, if you have questions, you can use Q&A at the bottom of your screen or chat. Either way, I will read them. So maybe, Rongchao, you can comment on the surface ligand. If you remove the ligand, is the structure going to change or not?
Yes, this is a very important and also very interesting thing. I would say if you remove 1 or 2 ligands, the structure gonna remain. Yeah, because if you remove 1 or 2 ligands, it's not that critical. You're not gonna introduce too much damage to the particle. But if you remove, let's say, 50% or even more ligands, yeah, I believe the structure gonna transform, gonna change. Yeah.
I see. So let's see. Looks like there's no questions from the audience. So maybe we can just stay on schedule and move to the next speaker by Yandong.
Thank you.
Thank you.
Yeah, thank you. Thank you very much, Rongchao, for telling us about that review. And of course, people who want to know more can go and read the review. But next up here, we are going to hear from Professor Yandong Yin from University of California, Riverside in the United States. And the title of his review is Encapsulated Metal Nanoparticles for Catalysis. So thank you, Yandong. Please take it from here.
Yeah, thanks. I hope everyone can hear me. And today I'm going to talk about the encapsulated metal nanoparticles for catalysis. And Professor Rongchao and also Professor Rongchao have already talked about the importance of metal nanoparticles for catalysis, and they can be used for really a broad range of reactions. And I also used this same example, gold on titanium, gold nanoparticle on titanium for CO oxidation. But I use this reaction to talk about the importance of size. Okay, apparently there's a magic size that works the best. Okay, and slightly larger than that, if you go to 4 nanometers, the activity disappears right away. Okay, so very small particles are very important. They have high surface area, and they also provide abundant coordinatively unsaturated sites, and they also provide opportunities for distinctive electronic structures. So that's why they are very active, and they can be also very selective. The challenge of these kind of metal nanoparticles is that they are usually used not really in solution, but on supports. Okay, so there's a sintering problem, especially if the reaction runs at high temperature. So this is our own example. We put the platinum nanoparticles on silica and oxide substrate, and you see that these two particles, and when we heat up to 200 degrees C, and you already see that these two particles get closer, 300 degrees C, they merge, they become larger ones. You can imagine if you have perfect size, when they merge, their size doubled, and then your catalytic activity disappears, right? And so that's a challenge. And in catalysis community, people already realize that, and they start to use so-called strong matter support interactions to stabilize the nanoparticles on the surface. So the problem here is that this strong matter support interaction is very specific to the materials combination. It's not general. So in the colloidal chemistry community, we actually try to address that. We try to develop methods to physically encapsulate metal nanoparticles and then try to stabilize them. So the purpose certainly is to promote sintering resistance, but at the same time, by wrapping these nanoparticles with a support material, we actually can create active matter support interfaces, and we also can control the encapsulating materials to provide additional control on this activity. So in our review article, we basically grouped the encapsulation methods into 3 categories. One is using basically inorganic nano shears, and second, we use nanopores, and third, we use organic capsules to stabilize all these particles. So I'm just going to go through these different methods very quickly. And so the first type is basically to use inorganic nano shears. And typically we use silica. Silica is well known for its solder chemistry, very easy to do, and room temperature reaction. Okay, and so the reaction is basically hydrolysis reaction of organosilane, and we produce silicate. And silicate is deposited on the metal surface, and then we form a coating, and then we encapsulate particles inside. And the challenge here is that this gold, for example, and silicate, they don't really like each other, so we actually need something, a primer or linker or a coupling agent to connect the metal surface and the silica. Okay, and people use different types of linkers or primers. For example, aminosilane, the polymer PVP, or thiolated PEG. And once you have those, and then the coating becomes very easy. Okay, but the challenge is that the system, this kind of process is limited to large metal nanoparticles, typically larger than 10 nanometers, and that's because of complicated hydrolysis and condensation reactions when you try to coat thin, smaller particles. Okay, and then people actually move the hydrolysis reactions to micelles, reverse micelles, so that we can coat really small nanoparticles with silica. And in this case, usually people do reduction reaction to produce these metal particles directly in these reverse micelles. They're actually called nanoreactors. Okay, So the reaction is limited inside the micelles so that the particle size can be controlled. And the hydrolysis reaction of organosilane can also be introduced here. And then they can we can achieve very thin coating in this case. Okay? And my group also extend this process to even smaller particles and with better control. What we did was basically instead of creating nanoparticles directly, we create precursors to nanoparticles. For example, in this case, gold oxide nanocrystal by precipitation reaction. And then this oxide actually has very good compatibility with silica, and we can coat the silica and with very thin, small thickness. And then after reduction reaction, we convert this oxide into matter. So because we get rid of oxygen in this case, so the particle can actually get even smaller. So by using this method, we can produce very small particles, 1.5, 1.8, 2.3, with very good control and very good encapsulation in the silica. And another oxide where we are known for encapsulation is titanium. And people use that just because this is photoactive, and people use that for photocatalysis. And so the process to coat titanium on metal nanoparticles is exactly the same. It's solder process. The difference is that the reaction here is very quick, very fast. And then you end up with free or heterogeneous nucleation of titanium particles, so they form their particles on. They don't really coat. Okay, so the way to address that issue is to use a chelating agent to slow down the hydrolysis, and so that we can coat the nanoparticles with the thin layer of titanium oxide. So people use ester acetone, ethylene glycol. This was our work, and citric acid. And or they can make directly react the chelating agent with the titanium precursor and form a new precursor for the coating. Okay, and as long as the hydrolysis reaction is slower, and then the coating can be done much controllable way. Okay, and another type of oxide is cerium oxide, and we're used as a support for catalysis. And in this case, people use different ways to encapsulate nanoparticles inside. And here I just show you two typical ways. One is this based on this self-assembly assist solder coating process. And so, for example, in this case, people start with palladium and coated with ligand MEOA. And then they introduce this cerium oxide and based on the absorption on the surface. And then they stabilize this with additional capping ligand, and then introduce controlled hydrolysis to convert the oxide into cerium oxide. Okay, and the good thing here is that the particles are very small, the coating is very thin, and by modifying the surface of alumina, they can actually introduce these kind of encapsulated nanoparticles onto the support of alumina. And they produce very good catalyst that can be very active for methane oxidation. Okay, another very clever way is to use this auto redox reaction, and people, for example, precipitate cerium 3+ and platinum 2+ and produce a precursor particle. And upon heating of this kind of precursor particle, and there's an auto redox reaction. Basically, a cerium 3+ become 4+, and platinum 2+ is reduced, become a metallic platinum. And then you end up with these clusters of cerium oxide with platinum nanoparticles inside, and very small. Okay, and the last example of inorganic nanoshear is carbon, and the way to produce carbon coating is also through typically conversion reaction. With, for example, we coat the particles with coordination polymer, in this case potassium tannic acid, and the original particle was ZIF, basically morphed particle, decorated with platinum nanoparticle. So we basically wrap them and then polarize the system, and then the polymer is combusted. ZIF actually is also combusted, and we produce platinum particles inside a capsule of carbon. Okay, if you do cation exchange, you can do that partially, and you can introduce cobalt into the system. And then if you do pyrolysis, you end up with another shear with the bimetallic nanoparticles inside. So if you do low temperature pyrolysis, you get amorphous carbon, but if you control the reaction at really high temperature, for example, 700 degrees C in this case, we can convert the coating into crystallized carbon, basically graphite. And then if you remove, for example, the template zinc oxide, and you end up with metal nanoparticles of palladium decorated inside a carbon nanotube. Okay. And so we also have other ways to encapsulate nanoparticles. For example, we load them into mesoporous materials. And in this case, people use impregnation method. This is a very typical one for introducing materials into mesoporous materials. So people use, for example, use surfactant assemblies as a template to produce a polymer matrix, which is porous because of these surfactants. And then they use impregnation method to introduce bimetallic precursors into the pores. And then after reduction, we end up with platinum cobalt bimetallic catalyst particles supported by this mesoporous carbon network. And there's also in-situ self-assembly approach, and you can introduce metal cations onto the block copolymer, and then self-assemble block copolymer into superstructures like spherical particles, and then evaporate solvent, and you organize them into three-dimensional ordered structures. After pyrolysis, you actually convert this block copolymer into carbon network, and in this case you have mesoporous carbon with oxide inside with platinum nanoparticles there. You can go further, you can pyrolyze in air, and then you can convert, or you can get rid of the carbon, and you end up with platinum nanoparticles inside tungsten oxide, for example, in this case, framework. And as you can see, the size can be very small. The size of particles can be very small. They are very stable within the framework. Okay, and Xerite is another type, and people use basically coordination chemistry to prepare a silane complex with metal cations, and then they add that into Xerite synthesis. And after hydrothermal reaction, you end up with a framework of Xerite containing these complexes, and then you do oxidation reaction, get rid of the organic species, and induce the formation of oxide, for example, and then use hydrogen reduction to convert the metal species into metallic state, and you end up with these loaded or encapsulated nanoparticles. Okay, and a new type of framework structure, morph, and we can encapsulate nanoparticles into morph as well. And then the typical method is also impregnation, and especially for large pore morph structures. And as the example shown here is the case people use so-called double solvent. And then basically the double solvent method is basically a mixture of small amount of water and large amount of hexane, and the water contains this platinum precursor, and so water can enter the pores of the morph, but you don't have extra for the outside, so you don't have a bigger aggregation outside, and so in this way you can produce really nice, very small nanoparticles within the framework. Okay, and this is a very similar method, and people introduce copper into the morph network, and then they actually use galvanic replacement reaction to break up this particle and change that into a copper palladium much smaller clusters. Okay, I'm not going to go through the details.
Yeah, one more minute.
One more minute, okay. And So people can directly code morph onto the matter structures as well. And there's a little complicated interactions between the nanoparticle and the morph precursor, so that they end up with very complicated structures, but encapsulation is possible. Okay. Last example, organic species, we can use dendrimers to stabilize the nanoparticles, and you basically functionalize the interior of the dendrimers, and then you complex with metal kinase after reduction, you stabilize them. Okay, and people also use organic synthesis to produce organic cages with a porosity on the surface. They can encapsulate the nanoparticles inside. Okay, so last, I just want to use 1 minute to talk about the advantages of encapsulation. Apparently, the first advantage is the stability. We can actually have very stable performance over a long time at high temperature. Okay. Second, this encapsulation brings the additional materials that wrap the surface, so we can control the porosity on the surface, and we can screen this, the reactants, the size of, based on their sizes. The smaller ones can go through, and you can have high reactivity. The larger ones cannot, and then you have really no reaction happening. Okay, and there's also enhanced electron transfer, because you wrap these particles. For example, in this case, we wrap them with a monolayer of carbon, and when they get in touch with these support, in this case carbon nanotube, and then the electron transfer is excellent, and then we can have very good performance in, for example, OER reaction. Okay, and there's also opportunities for organizing this tandem catalysis. You have nanoparticles inside, and one type of nanoparticles inside, and then you have these channels, mesoporous channels. And then you have another catalyst outside, and you can do sequential reactions, and then you can enhance the selectivity, for example, in this carbon dioxide to C2 and C4 hydrocarbon. Okay, and so perspectives, I think we can do much more on the synthesis to popularize the encapsulation methods, and to make the nanoparticles better, and with better size shape control, and also the encapsulating materials we can make with more control on that. And large scale production, and we currently our synthesis is smaller, and we, for practical reactions, we actually need a large amount. We can have better understanding on the structure catalytic property relationship. We can extend the scope of the catalytic applications. Okay, and with that, I'll just stop here, and I'll be happy to take questions.
Thank you, Yandong. So there's one question posted already.
Okay.
And basically, this person wants to know if you can, let me see, could the approach used for serial encapsulation be applied to metal nitride nanoparticles?
Yeah, I think, let's just go to, sorry, my screen is frozen. I think in general, yes, and then certainly you have to functionalize the nanoparticle. And for example, the first one I mentioned was based on a surface adsorption, and you have to absorb the ligand onto, not the ligand, the precursor onto the surface of the particle, and they use the I think it was carboxylic acid group to connect the precursors. So that's why you have to functionalize the nanoparticle surface in order to do that. But in principle, I think that's very possible.
Okay, thanks. So Rongchao, if you are still online, here's a question for you from the audience.
Yeah.
Okay. So basically the question is, what's the proper way to remove the surface ligand effectively?
So there are quite a number of ways. I mean, the traditional way is, of course, thermal treatment. but that's not the best way because typically in this aggregation, like Professor Yandong talked about in his presentation. Some other ways, for example, you can use sodium hydroxide to gently remove ligand, and also the redox way. Yeah, so for example, if you crank up the voltage to negative, yeah, sufficiently negative, so you're gonna be able to kick out some ligands. Yeah, so for details, I think yeah, you can go to the review article. These are general ways you can practice to remove the ligands.
All right, thanks, Rongchao. So let's stay on schedule and move to the next presentation.
Okay, and thank you, Yandong, for a very excellent presentation. So next, the next speaker is Professor Baran Eren from the Weizmann Institute in Israel, and he will be telling us about, the title of his review is High Pressure Scanning Tunneling Microscopy. So welcome.
Yeah, thank you for the introduction. Let me use this opportunity to thank all the guest editors who compiled this special edition. My talk is going to be about high pressure STM. I prepared this together with Michael Salmeron from the Lawrence Berkeley National Laboratory. Let me start by frame setting. This is a surface science study, but it's not done in traditional surface science conditions. Now, surface science is the field of elucidating a variety of physical and chemical processes on a variety of surfaces. It's traditionally done in ultra-high vacuum conditions, that is 13 orders of magnitude lower pressure than ambient air. And this is required because of several reasons. For cleanliness of the surfaces is the first reason, because most of the techniques we use are not applicable in the presence of gases or liquids is the second reason, so on and so forth. Now, this is of course a very important field. We owe our current understanding of solid surfaces to decades of surface science studies done in ultra-high vacuum conditions, and it led to the Nobel Prize in Chemistry in 2007. However, as we know, real reactions take place in the presence of gases or liquids. Now, there are two problems. The first problem is thermodynamics. So in traditional surface science studies, we are actually probing the surface at a different point in the thermodynamic phase diagram. So when we probe the surface in the presence of gases, there's going to be an equilibrium shift. And the second problem is because of our choice of pressure and temperature, the chemical potential is virtually 0 electron volts. So if there are some kinetic barriers, we'll not be able to overcome these kinetic barriers. Whereas in the presence of gases, and let's say at room temperature and above, there's going to be a certain energy, and we can actually overcome the kinetic barriers. So this is referred to as the pressure gap or pressure temperature gap between science and technology. Now, the other gap that has been referred in this mini symposium is the materials gap or the complexity gap. Now, let's talk within the context of heterogeneous catalysis. The most active part of the catalysts we use today are metallic nanoparticles, but the surface science studies and also our studies are actually done with single crystals. Now we are simplifying our materials, so we are, let's say, instead of using this facet, 111 facet of this nanoparticle, we model it with a semi-infinite 111 surface. Same for the 100 facet, we model it with the semi-infinite 100 surface. Now, the disadvantage is, of course, it's less realistic material, but the advantage is that we can do atomically resolved imaging, or we can have information at the atomic level. So there is a trade-off here. Basically, we have to choose one. Now, in the last few decades, let's say in the last 2 decades, many methods have been developed that make surface science applicable in the presence of gases. I work quite a bit with ambient pressure X-ray photoelectron spectroscopy technique and IR spectroscopy techniques that have been specially adapted to be applicable in the presence of gases. These are spectroscopy techniques, and frankly speaking, they're more widely used than microscopy techniques. But microscopy techniques have their own benefits, and most importantly, they're images in real space, so they show you what's happening on your surface. And scanning tunneling microscopy, we know it can atomically resolve the surfaces very well. Now, I'm going to show 4 examples, which I personally think are very important historically and for really better understanding of what's going on at ambient pressures. The first example is from Flemming Besenbacher's group from the Aarhus University in Denmark. It's on carbon monoxide adsorption on platinum 111 surface. So carbon monoxide and platinum, this material system is the Drosophila of surface science. Like maybe half of the surface science studies in the literature were done either with carbon monoxide and with platinum. But we can see already that at ambient pressures, the results are quite different than what people get at traditional surface science studies at ultra-high vacuum conditions. Now here, what you see is the STM image of platinum 111 surface in the presence of either 0.01 torr or 720 torr of carbon monoxide. And in the image here, each bright structure corresponds to one CO molecule. And you can see that there is a quite dense structure of carbon monoxide on the surface. So that was actually the most important outcome of this work, that actually one can reach a coverage of carbon monoxide that was not reachable, that was not reached before in UHV studies. Now here, this carbon monoxide also forms ordered structures on the surfaces. And because the periodicity of carbon monoxide and the periodicity of platinum 111 surface is different, it also forms a moire pattern. But the most important thing is not the moire pattern. The most important thing is that the structures, the adsorbate structure of carbon monoxide is quite dense. This was not observed before. And this was back in 2004. Now, in 2010, something new was observed for the first time. We observed that a surface which is supposed to be very stable was actually not stable in the presence of gases. Now, in this example, again, it's carbon monoxide on platinum. This time, it's a vicinal surface. That means that you have the 111 surface, same as before, but there's a miscut of 10 degrees. So this is the illustration of the surface on the left-hand side. So you have for every 6 atoms on a terrace, you are going to have a monatomic step, a small step. So that gives you 10 degrees miscut. And this is how it looks like in ultra-high vacuum conditions under STM imaging. So it's a large-scale STM image, actually. But this is satisfactory for the purpose of this work. And you see that once carbon monoxide is dosed, already at low pressures, the width of the terraces is now double, and also the height of the steps are doubled. Now, this is already interesting by itself. Actually, the stability of the step structures is already interesting by itself, but we see that there is a change. They are a bit destabilized, basically, in the presence of gases. Now, when you go to even higher pressures, you see that they're completely unstable. They break up into clusters in the form of, it's not well resolved in these images. They're triangular clusters. In studies later on, people actually show these triangles, both in the presence of gases and in the presence of liquids. So now it's the first time that a surface was shown that it breaks up into clusters in the presence of gases. And what I don't show here is that there is another surface, platinum 332 surface, that's basically very similar to this platinum 555 surface. Again, you have a platinum 111 surface, and again, there is a miscut of 10 degrees. But this miscut is now in another direction, and instead of this microfacets or these steps of 100 type, you have 111 type of steps. Interestingly enough, at low pressures, there was no step doubling for the platinum 332 surface, and at higher pressures, there was clustering, but the clustering was in the form of parallelograms. Now we are in year 2016. This is a work of mine, And it's the first time that now we show that clustering does not only happen on the stepped surfaces, which are a bit less stable, but it can also happen on the most dense and compact 111 surfaces of, let's say, FCC metals. This time it's on copper. And what you see here is an image in ultra high vacuum conditions, has been imaged, hundreds of times before me. You see this large terraces separated by monatomic steps, large meaning that the terraces are like hundreds of nanometers squared. And if you zoom in, you can atomically resolve them, of course, because we have an STM. But now we see that in the presence of gases, let's say in the Thor pressure range, something is covering the surface or whatever is, and as we increase the pressure, whatever is covering the surface is increasing in size and density. And if you go to 100 Thor, then the entire surface is covered with these structures. These are copper clusters. So the copper surface is broken up into clusters in the form of, well, different 3-atom or 19-atom clusters at this pressure. And you can see actually a 19-atom cluster here, which is 6-fold symmetric, which is a building block of larger clusters. But the importance here is that we show that even the 111 surfaces, which are supposed to be the most stable, can become unstable in the presence of gases. And the reason is, of course, well, you can of course explain this with energetics. The formation of these clusters cost us some energy. But after we form these clusters, the carbon monoxide adsorption energy will be significantly higher on the newly formed edges compared to the terraces, flat terraces, so that the total energy gain through adsorption of carbon monoxide on this edge side is going to be more than the formation energy of the clusters. And copper or gold are actually a bit special in this case because they are low cohesive energy metals. So for other metals like maybe platinum, you could maybe see this if it's energetically favorable to form, but you have to go to higher temperatures. But for copper, already at room temperature, this can happen. Now, the final example I would like to show is going to be an example of a reaction. Reaction studies are much more difficult to perform compared to adsorption studies, but now they're also possible to perform. I will briefly mention why they're very, very difficult to perform in my last slide. But here you see an example of carbon monoxide hydrogenation on a cobalt surface. So this is Fischer-Tropsch synthesis, so synthesizing linear hydrocarbons, which can be used as fuel. And you can see this is really actually at the industrial reaction conditions at high temperatures and over 1 bar pressure. And you see on the cobalt surface the formation of these structures. And here you can see a zoomed in image. And these are actually these structures that actually are resolved, are attributed to the formation of linear hydrocarbons. So these are your products actually. And you can see that they're mostly perpendicular to this step edges. Now this paper that is discussed in the review article also mentions the reaction mechanism. Now we know for a fact actually from reaction studies on cobalt nanoparticles that the surface is active in producing methane in the first 2 minutes, which is completely undesired. But after 2 minutes, the selectivity switches from methane to desired long chain linear hydrocarbons. So the model here suggests that the terraces are active in formation of methane, whereas the step edges can also do CC coupling. So that's where actually linear hydrocarbons start to form. But as the reaction proceeds, these linear hydrocarbons, they start occupying also the terrace sites. And because the terrace sites are occupied after a certain point, as is actually captured in this image, then there is no active site available for methane formation anymore. That's why the selectivity of cobalt catalyst changes after 2 minutes. Now, these are all the examples I wanted to show. And in our review paper, we actually we review 50 different studies. But this is also the total number of HPSPM studies in the literature, and that's not a lot. Now, compared to a spectroscopy technique, ambient pressure photoelectron spectroscopy, so this is actually statistics from 2019. So I guess it's around 1,000 now. It's 20 times less output. Now, what is the reason for this? First of all, these are a bit more difficult studies to perform. Technically, actually, they're not that difficult to perform, but to get atomically resolved images is quite challenging. Already in traditional STM is challenging, and in the presence of gases, it's even more challenging. But now these setups are also commercially available. So I actually see that more and more groups are buying these setups, and they're doing atomically resolved studies at ambient pressures. Now, the merit of such studies or the impact of such studies is that you get atomically resolved images. Okay, I mean, this is very important. It's actually, in my personal opinion, it's equivalent to actually hundreds and hundreds of spectra that are obtained, and there are not many techniques that can provide such information at the atomic level. And the main challenge of this technique, and it still is the main challenge, is really heating. The problem here is that if we heat our surface, because of conduction or because of convection of the gas phase molecules, we also start heating other parts of the microscope, especially the piezoelectric materials, and this induces some thermal instability, sometimes makes it really impossible to image. So this remains to be the main challenge, but if this can be overcome, so if we can find a permanent solution where we can work at, let's say, ambient pressures or even atmospheric pressures, and while heating our surfaces, then I think it will also become a major tool similar to the spectroscopy techniques that I mentioned. Thank you very much for listening.
That's great. Thanks for being on time. So let's see any questions. So when you run the STM under ambient pressure, can you still achieve atomic resolution?
Yes. This is atomically resolved images. So, and if you don't have clustering, and if you don't have very strongly adsorbed species, you can still you can see the atomically resolved image of your surface. Yes, not all studies get atomically resolved images. I would say of the 50 studies, maybe 20 of them are atomically resolved. It's challenging. You need a surface that's not very mobile, like while working with hydrogen or while working, well, hydrogen, there are some examples, but water, it's actually, I didn't see any atomically resolved images. Usually with, I would say that around 60% of studies are with carbon monoxide, and that's actually rather easy to atomically resolve.
Thanks. So let's see. Looks like there's no question from the audience, so we can move to the next presentation.
Okay, great. Thank you, Baran, for an excellent presentation. It's a very powerful technique. So the next talk will be given by Professor Janis Timoshenko, and he's from the Fritz-Haber Institute of the Max Planck Society in Germany. And the title of his review is In situ operando electrocatalyst characterization by X-ray absorption spectroscopy. So welcome, Janis, and we're looking forward to your talk.
Thank you so much for the introduction. I hope you can see my slides right now. And,
yes, we see them. They're coming through very well.
Let me know. Yes. So I will be talking about catalysis and the problem of determination of structure of catalysts. So in general, understanding how the catalysts work is quite a complex problem. In part, it's because the catalytic behavior and functionality depends on often quite subtle details of the catalyst structure and composition. For example, copper-based catalysts for CO2 electroreduction can produce a number of different products, so CO2 can be converted into a number of different chemicals, but the selectivity of the catalysts depends strongly on the properties of the catalyst, such as its oxidation state, surface composition, crystallographical structure, particle size, and so on. And all these parameters also can change under reaction conditions. So sometimes these changes are quite pronounced, quite visible, sometimes they are more subtle. But in any case, if you want to really understand how the catalyst works, or how can we improve its performance, it's really important to be able to look at the structure and the composition of the catalyst under working conditions. And for that, we need to have some operando spectroscopical tools. And X-ray absorption spectroscopy is one of such really nice methods for this purpose. So in X-ray absorption spectroscopy, we are measuring absorption coefficient for X-rays. as a function of the energy of incident X-ray photons. And these experiments can be performed directly by just measuring attenuation of X-rays inside your sample, or indirectly by measuring the intensity of fluorescence, which is proportional to the absorption coefficient. And clearly, in the context of operando studies, an important benefit of X-ray absorption spectroscopy is the high penetration depth of X-rays, which means we can not just study our samples in air, but also in quite complex environments, such as electrochemical cells. And one approach could be that we can deposit our catalyst on carbon electrode, and then this carbon electrode is used also as a window, both for incoming incident X-rays, as well as for X-ray fluorescent radiation. So when we talk about X-ray absorption, so what happens actually? So incident X-rays are exciting deep core electrons in our material from the deep core level states to some available as higher energy states. And when the energy of X-ray photon matches the energy of these core level electrons, we see a significant rise in the absorption probability, which we denote as absorption edge. And then the fine structure above this edge is due to the transitions of these core electrons to localized or delocalized states. And in particular, in case of transitions to delocalized states, these excited photoelectrons can also interact with electrostatical potentials of neighboring atoms, and in that way, information not only about the electronic state of our atom, but also about arrangements of neighboring atoms is recorded in this fine structure of X-ray absorption spectra. So in general, we can split this X-ray absorption spectra in two parts, X-ray absorption narrow edge structure or XANES, and extended X-ray absorption fine structure or EXAFs. And the physics in both regions is the same, but approximations which we need to describe both these two regions are different. And also different information can be learned from XANES and EXAFs parts of absorption spectra. In particular, XANES is mostly sensitive to electronic properties, to oxidation state of the material, while EXAFs is mostly sensitive to the geometry of the material. So what's important here in what is actually a very nice advantage of X-ray absorption spectroscopy over other techniques is that from a single experimental measurement, we can get quite rich information about the structure and properties of our catalysts. So we can look at quite subtle things such as changes in interatomic distances due to thermal expansion or due to interaction of metal atoms with adsorbates. Or from the same data, we can also look at nanoscale structure of the catalyst and look how particle sizes and shapes changes under all reaction conditions. And of course, we can look also at bigger picture, how crystallographical phase or oxidation and reduction happens, which involves the entire sample. And finally, when we couple XAS with spatially resolved data acquisition methods, we can use the X-ray absorption spectroscopy to map distributions of different species within our macroscopic chemical reactors. So a lot of possibilities here for studies of catalysts. So in the remaining part of the talk, I will illustrate the power of X-ray absorption on a few selected case studies, mostly in the context of CO2 electroreduction, but similarly it can be used to study many other electrochemical processes. But in the context of CO2 electroreduction, one particularly controversial topic is the role of oxidized copper species for a conversion of CO2 into multi-carbon products such as ethylene or ethanol. So in general, CO2 electroreduction occurs under quite negative applied potentials, which means that we expect our catalyst to be mostly reduced, mostly metallic under reaction conditions. At the same time, in literature, there is increasing amount of evidence that oxidized copper species can be actually beneficial for CO2 conversion into products like ethylene or ethanol. In particular, the study by Mystery and others have focused on copper foils, which were treated by oxygen to plasma and demonstrated that after such treatment, the selectivity of CO2 conversion to ethylene is significantly increased, something that was not observed after treating the foil with hydrogen plasma, for example. So it means that really on top of these morphological changes which we induce in our catalyst by plasma treatment, also the presence of oxides, similarly induced by the oxygen plasma treatment, can be important for understanding the catalytic properties. And X-ray absorption studies can provide additional important information about the stability of such oxide species. In particular, in this study of oxidized copper foils, in as prepared state, means after treatment with oxygen plasma, Fourier transformed EXAF spectra show us typical features of oxidized copper. And to some extent, these features are preserved also after exposure to reaction conditions for 15 minutes. So we still see this clear, nice peak corresponding to copper-oxygen bonds. At the same time, there is growing contribution of metallic copper as seen by this next big feature. So after prolonged exposure to reaction conditions, however, no more signature of oxide species can be resolved. But one needs to keep in mind here that this particular sample maybe is not the most convenient system for X-ray absorption studies. And the reason for that XAS is spectroscopy method, and similarly as other spectroscopy methods, it's a sample averaging technique, which means that the information which we are collecting is averaged over all species in our sample. And if our sample is bulk-like material, as in this case, there is still possibility that some fraction of oxide species exists near the surface. We just don't see it in our sample average data. That's why quite instructive were a follow-up study, which was also carried on pre-oxidized copper catalysts for CO2 electroreduction, but in this case, these catalysts were prepared in form of size and shape selected copper cubes. So in this particular case, the surface to volume ratio is much higher, so we are more sensitive to the surface processes when applying sample averaging methods like XAS. And also in this case, both in XANES and EXAFS, one can see typical features of reduction of copper under reducing CO2 electroreduction conditions. But the interesting conclusion that is after even 3 hours under reaction conditions, we still see a quite significant fraction of copper oxide present. 10–20% of copper oxide still remains, which allow us to say that at least it is worth to consider that this oxidized species may be important for explaining the catalytic activity for copper and its activity for production of multi-carbon products. Clearly, it's not always about only about oxidation state, and other properties of the catalyst are also important for understanding its catalytic properties. For example, one common strategy for improving the catalytic properties of copper-based catalysts is to alloy copper with secondary elements, secondary metals. The idea here, one of the ideas here is that by alloying, we can change interatomic distances due to the lattice mismatch between copper and this secondary metal. And guided by DFT simulation, we can also find such interatomic distances which favors specific absorption energies for our key reaction intermediates for CO2 electroreduction, and we can predict for which composition of alloy we should see the most pronounced CO2 electroreduction activity. However, it's important to note that all such predictions or the actual presence of such bimetallic alloy motifs should always be validated by experimental measurements, since both alloying and de-alloying can take place under reaction conditions. And in this particular case, XAS gives us a lot of important information because both XANES and EXAFS regions of absorption spectra are actually quite sensitive to interatomic distances. For example, it was demonstrated in this study by Friebel, where copper monolayers on gold substrate were investigated under applied potential, and in situ formation of copper-gold alloy was detected. But also interatomic distances are not just the whole picture. In some cases, for example, for silver-copper system, what's important to see is just whether there is neighboring copper and silver atoms in the system, because these copper and silver proximity effects are believed to be quite important for CO2 conversion again to these multi-carbon products. And again, presence of such bimetallic structures should not be taken for granted, especially for systems like silver-copper, where unlike copper-gold system, the miscibility of silver in the copper is quite low. So we cannot really be sure in advance that there will be any meaningful amounts of copper-silver alloy present in our sample under working conditions. And EXAFS, or X-ray absorption spectroscopy in general, is quite good in answering this kind of question. And this recent study, which focused on copper cubes decorated with silver nanoparticles, it was really demonstrated that silver-copper bonds are really present, are visible in EXAFS spectra, and moreover, these contributions are getting more pronounced under reaction conditions. And of course, it's also nice to see that this presence of the silver-copper bonds was nicely correlated with the enhanced activity of CO2 conversion to multi-carbon liquid reaction products. Also, importance of the time-dependent structural changes in bimetallic CO2 electroreduction catalyst was highlighted in our own recent study about copper-zinc nanoparticles. So here we investigated size-selected copper-zinc nanoparticles with sizes of about 5 nanometers, and we observed quite interesting time-dependent trend in their catalytic activity. Basically, reaction products after 5 hours were completely different than the reaction products after 1 hour under reaction conditions. So clearly something was going on with the catalyst, it was changing in the reaction conditions, and we used X-ray absorption to understand what's going on. So first, again, we started with Xene's analysis, which provided us with important information about oxidation state both of copper and zinc. And in as prepared samples, both these metals are oxidized, but they are reduced under reaction conditions. What's interesting here is that the reduction rates for copper and zinc are quite different. So copper is reduced almost instantaneously, while for zinc, this process is much slower. So now we want to know what happens with copper environment, which is supposed to be the active species here during the slow reduction of zinc. And to answer this question, we now look at EXAFS spectra. So challenging studies of copper-zinc alloys or other alloys which consist of metals which are neighbors in the periodic system is that unlike copper-silver or copper-gold case, here the contrast between copper and zinc partial contributions to EXAFS spectra is quite low, so it's not so easy to tell them apart. At the same time, we still can distinguish between copper-rich and zinc-rich phases of the material if we manage to extract information, accurate information about interatomic distances, because these are expected to be different in copper-rich and zinc-rich materials. So to extract such accurate information, in this case, we actually relied on quite advanced data analysis approach based on machine learning and neural network analysis, which allow us to map directly or to establish a relationship between spectral features in our EXAFS spectra and the entire bond length distribution function or radial distribution function. So radial distribution functions for our copper-zinc nanoparticles are shown here. So here we see the radial distribution function for the as-prepared catalyst, and it's very similar to the local structure of copper hydroxide. Basically, see a contribution of copper-oxygen bonds, but also some copper-metal contributions. So when we apply the potential, the copper oxide contribution is gone, and we are left only with metallic fraction. But that's not the end of the story. And if you look carefully enough, after 7 hours under reaction conditions, we observe that all these peaks, all the interatomic distances are shifted towards larger interatomic distances, which is clear fingerprint of alloying, which takes place within about 6-7 hours in this material. And it's nice to see that this characteristic time for these changes is actually matching very well the characteristic time of changes in catalytic properties that we observed in the previous slide. So these two processes clearly are intimately linked. So this particular study illustrates quite nicely possibilities provided by these data advanced analysis approaches and machine learning for interpretation of subtle fingerprints of in our EXAFS spectra due to transformations of our catalyst under reaction conditions. But furthermore, the abilities of XAS during the last years are further extended by advances in the instrumentation. For example, recently it was demonstrated that time-resolved XAS studies are now possible in an electrochemical environment with sub-second time resolution. And in this proof of principle work, for example, it was demonstrated that both Xene's features and also geometrical structure descriptors such as metal-metal and metal-oxygen coordination numbers can be tracked with excellent time resolution. And what's more importantly, different characteristic time scales observed for evolution of these different features in our XAS spectra can now be linked to different distinct steps into quite complex overall picture of processes which takes place on the surface of the catalyst during its exposure to potential and the electrolyte. In this particular case, we can try to single out now the contributions of processes like chemisorption of certain adsorbates, oxidation of the catalyst surface, or the restructuring, changes in the geometric structure of our catalyst nanoparticles. And clearly also the ability to collect spectra quickly is very beneficial also for spatially resolved studies. So here we can use a focused X-ray beam to scan over large areas in our sample and collect X-ray absorption spectra in each pixel in each point of our sample. And this allows us to investigate the importance of heterogeneities in our catalytic system. For example, investigate the role of cracks in our electrodes. And it can be linked, for example, using X-ray absorption as spectra analysis to the locally enhanced platinum oxidation state, which again may have important consequences for explaining the catalytic performance of the overall electrocatalytic system. And finally, also the X-ray absorption method itself is getting increasingly more sophisticated. So now we can not just look at the total intensity of fluorescence, which we measure during our experiment, we can install additional analyzers and detectors and measure the spectrum of the X-ray fluorescence. And in that way, we have a method which is called a resonant inelastic X-ray scattering, which is basically a crossover between X-ray absorption and X-ray emission spectroscopy, and is a very powerful approach to study in detail the electronic structure of the material and excitations in the material, and can be used, for example, to distinguish with much better accuracy between different species present under reaction conditions, or to study interactions between a metallic catalyst and the adsorbates. So with that, I would like to conclude, basically, and I believe that these advances that I have demonstrated briefly in data analysis and also in the instrumentation, coupled especially with the similar advancements in other operando techniques, is really a solid and nice basis for the future development of the method and provides a new exciting possibilities for using X-ray absorption spectroscopies for tracking quite subtle and quite complicated structural and chemical transitions in our working electrocatalysts. Yeah, with that, I thank for your attention, and I'm ready for your questions if there are any.
All right, thank you. Here's a quick question for you from the audience. So did you also use theoretical methods to model X-ray absorption spectrum?
Yes, sure. One of the another great benefits of X-ray absorption spectroscopy is that actually spectra can be modeled quite well. So especially for EXAFS region, the mathematics underlying the oscillations is understood quite well, so we can model them very accurately. For a near-edge structure, for xenes, it's a bit more complicated, so it's still possible to model them and use it to establish the relationship between spectral features and structure. As a result of such modeling, but the accuracy typically is a bit lower and the calculations or simulations are a bit more sophisticated. But yes, that's an important advantage of this method in its application for quantitative studies.
Great, thanks. So typically for this kind of measurement, it's like an in-sample measurement. So basically information you collected is from all different types of atoms, different particles. So you basically just average all of them to fit the spectrum, right?
Right, yeah, that's an important actually limitation. Also, I briefly mentioned in my talk that it indeed is, as any other spectroscopic method, it gives you the average picture, which is limitation, of course, because if your sample is complicated, which is normally is, so it has a mixture of different species coexisting, you need to account for that into your analysis. On the other hand, it also gives you maybe more honest overview of what's happening with your sample. So you don't focus on one particular small region in your sample, but you get information about the entire catalyst and see how it can be correlated with its catalytic performance.
All right, thanks. So yeah, it looks like we're doing well in terms of time, Sharon. So I'm going to hand this to you.
Yes, so I want to thank all of you for attending this inaugural symposium for the Chemical Reviews Thematic Talk Series. I want to especially recognize our guest editors, our speakers, the 4 speakers today, the authors of this thematic issue, and of course, all of our listeners out there. And if you want more information about any of these topics you heard about today, then please read the reviews in this thematic issue. It came out in January 2021, and these are only 4 of many reviews that are in this thematic issue. And we hope to see you at one of the future symposia that we are going to, I think, Marcus, you're going to post that on the screen there. And so we have an exciting schedule coming up. Every other month we're having one of these. And these are the topics you'll see. We have quantum materials, drug resistance, machine learning, and gold chemistry, all coming up this year. So please continue to come to these and tell your friends. And let us know if you have any suggestions for how we can make this a better experience. But again, thank you to everyone who participated in this. We really want to use chemical reviews as to have as a means for education and outreach to teach the excitement of these various topics to the community and to really highlight some of the exciting work that's going on worldwide. So thank you very much to everyone, and hopefully we'll see you on Friday, May 14th at the Quantum Materials Thematic Talk Series.